As a next step, and let's think about that extreme cases. And extreme case means that let's think about the strong magnetic field limit. Strong magnetic field case, and there are two cases. One is that the G-man energy, G-man shift by applying magnetic field, and the other one is the fine structure shift. Fine structure shift means coming from the relativistic effect and the spin-up coupling. But here, because magnetic field G-man energy is proportional UVB and MJ and GJ. So under the it is the G-man energy. And strong magnetic field means that G-man energy is higher than the fine structure. Yeah. Fine structure energy shift, G-man energy is higher than the fine structure energy shift. So, and because secondly, because magnetic field is so strong, and the perturbation theory is not valid, because in perturbation energy basically it means that perturbed Hamiltonian is weak comparing to the unperturbed Hamiltonian. So it is perturbation is not valid. So, and let's going back to the G-man Hamiltonian. And G-man Hamiltonian was that here mu b over h bar and GLLG plus GESG, and it is we should think about the zeroth order, not the perturbation calculation, because perturbation is so high under applying strong magnetic field. And also fine structure can be think about as a perturbation, and because fine structure is small comparing to the G-man energy. So in this case, perturbation is not valid only for the G-man energy, G-man effect. But and fine structure is fine structure Hamiltonian is the perturbative term. So here, because in the energy is that the Bohr energy plus G-man energy, so the energy case, energy En0 case is that Bohr energy is that minus Rydberg over n square, and the G-man energy is that NLS ML MS and HG prime NLS ML MS. So it is that the G-man energy correction, is that UVB over H bar. When you apply these matrix elements for the LG here, then this LG apply to the magnetic quantum number H bar ML, and also SG apply to the H bar MS. and the gyromagnetic ratio 1 and 2. So it is that GL ML H bar and plus GE MS H bar. So it is H bar cancel. So UBB and ML plus 2MS case. And here, basically, and the Giemann Hamiltonian is well defined because it is not a perturbation. It is not a perturbation of this in this case, and also it is a zeroth order. In the zeroth order Giemann energy, it is very well defined. But we should think about that fine structure. Fine structure Hamiltonian is the perturbation. So, and there are two kinds of energy. One is that spin-orbit coupling. Spin-orbit correction should be perturbative treatment. So, and spin-orbit coupling can be write down as the first order perturbation, and the first order spin-orbit coupling Hamiltonian is that NLS ML MS and a spin-orbit Hamiltonian and the NLS ML MS basis. So we already calculated the fine structure in the previous case. So in the result is that E square over 8 pi epsilon 0 m square c square and NLS ML MS and 1 over r cube L dot S and the spin-orbit coupling in NLS ML MS. So from the previous calculation, the result is that here E square over 8 pi epsilon 0 m square c square, and also and the orbital radial part 1 over r cube, and the radial part is that NL expectation, and also N coming from the orbital radial function. So it is L S ML MS, and the L dot S it can be transformed like a ladder operator, 1/2 L plus S minus plus L minus S plus LG SG, and the basis also L S ML MS. So this ladder operator then is not diagonal matrix element, and it is we call it as a ladder operator. Ladder operator is not diagonalized because ladder operator increase the quantum number or a decreased quantum number, and the basis is the same, but this ladder operator increases MS here, and the S minus decreases ladder operator MS, so it is not diagonalized anymore. And so only so off diagonal component of this one and zero because of the orthogonality, and also only survive as the LG and SG. All right, so only LG and SG survived. Then let's copy this. And also only LGSG, and LGSG the quantum number MLMSH bar square. So and the result, the final result is that 1/2 alpha to the 4 MC square MLMS over N cube L plus 1 half, L plus 1 case. And also it is a fine structure, fine structure spin-orbit coupling Hamiltonian, perturbed Hamiltonian. Fine structure is that relativistic effect. Relativistic effect plus spin-orbit coupling, and the relativistic effect also. So fine structure first order energy is that 1 half alpha to the 4 mc square, then relativistic effect to the 3/4 n to the 4, and also spin-orbit coupling in the in above case, and also L plus 1 minus ml ms divided by n cube L plus 1 half L plus 1. Yes, so it is energy correction for the relativistic fine structure. Fine structure can be considered as the weak perturbation, and the Zeeman energy is not perturbation anymore. Here in the strong magnetic field case, and we only consider for the ML and MS, this Hamiltonian LG and SG apply to the LG apply to the ML, and SG apply to the MS. So it is a well-defined energy eigenvalue is coming out. So it is very simply write down a Zeeman energy shift. But in previous case, and it is not defined, because in previous case, we used the projection theorem for calculation of the LG and SG case. Here in this case, and the basis is not uncoupled basis, but here it is a coupled basis. It is spin-orbit coupled basis. When you think about the spin-orbit coupling, and this magnetic quantum number is not well defined, it is not a good quantum number. So, and the total quantum number, total angular momentum is a good quantum number. So when we apply to the this coupled basis, and also we should think about that this kind of projection theorem. So it is the total angular momentum calculation is well defined, but it is single orbital where the spin magnetic quantum number is not well defined. So we use that the projection operator. But in the strong magnetic field, and here we do not think about that. Here we treat this Zeeman energy as that ground state. So in this case, and the basis uncoupled basis, not J but L and S. So it is it is well defined that ML and MS is a good quantum number. That is the differentiate between the projection and not projection.